During nearly 45 months of operations on Mars, Perseverance recorded thousands of hours of audio. Most of the data consisted of wind noise, wheel sounds, and the laser pulses used to analyze rocks. But hidden within that vast collection of recordings was a completely different type of signal. It lasted only for a brief moment before disappearing. After years of analysis, researchers identified a total of 55 occurrences of the same signal. Perseverance's microphone was never designed to search for this kind of phenomenon. Many explanations have been proposed, but no hypothesis has fully accounted for everything the microphone recorded. If the source was not located on Perseverance itself, then what produced these 55 signals in the Martian atmosphere? The first signal did not appear to be a major discovery. It was buried within the audio data that Perseverance transmitted back from Jezero crater, where the rover is investigating rock layers believed to be remnants of an ancient environment on Mars. The microphone on SuperCam was not designed to search for mysterious atmospheric phenomena. Its primary mission was much simpler. When SuperCam fires a laser pulse at a rock surface, the energy from the laser creates a tiny plasma cloud and generates a brief sound. By analyzing this sound alongside spectroscopic data, scientists can gather additional information about the composition and structure of the target material. After years of operations, most of the common signal types found in the audio data had already been identified and classified. But while reviewing the data, researchers noticed a completely different group of signals. They appeared as extremely brief pop or crackle sounds. Each event lasted only a moment before disappearing. They did not form long sequences. They did not repeat periodically. They did not resemble wind, nor did they match the sounds produced when the laser interacted with rock. If they had appeared only once or twice, they might have been dismissed as random noise. But as the dataset continued to expand, the number of similar signals began to grow. Eventually, the number of confirmed events reached 55. That created a rather unusual situation. Among thousands of hours of recordings, 55 events are too few to immediately establish a clear phenomenon, yet far too many to be dismissed as random interference. Each signal shared enough characteristics to be classified within the same category, suggesting that they may have originated from a common source. These signals were not distributed evenly throughout the dataset. They tended to appear during certain periods rather than being scattered completely at random. But before considering any explanation involving the Martian atmosphere, scientists first had to answer a more fundamental question. Was the source located on Perseverance itself? The first suspicion fell on SuperCam's microphone. This instrument had been operating continuously for years under conditions of extreme temperature fluctuations, fine dust covering its surfaces, and an atmospheric pressure averaging only about 6 to 7 millibars. Any sensor functioning for years under such conditions is naturally the first thing investigators examine. But when the research team compared the signals against the instrument's engineering data, they found no evidence that the microphone was malfunctioning. Its performance remained stable, and the mysterious signals did not appear in the way a faulty sensor would typically behave. As the possibility of equipment failure was gradually ruled out, attention shifted to the rover's mechanical systems. Perseverance is a machine weighing approximately 1,025 kilograms, containing dozens of motors, drive mechanisms, and moving components that operate almost every day. The wheels, the robotic arm stretching more than 2 meters in length, the instrument mast, and numerous scientific mechanisms all had the potential to generate sounds that the microphone could detect. The research team began comparing the timing of each signal with the rover's detailed activity logs. They checked whether the wheels were moving, whether the robotic arm was collecting samples, and whether SuperCam or any other instrument was operating at the exact moment a signal appeared. Once again, the results failed to provide the answer they were looking for. Many of the signals occurred when Perseverance was performing virtually no significant activity. Some were recorded during periods so quiet that no mechanical operation could reasonably account for the type of signal being observed. No operational pattern within the rover matched the timing of the events. The next hypothesis involved physical impacts from the surrounding environment. Although Mars has a very thin atmosphere, fine dust is constantly carried by the wind and collides with equipment on the surface. At first glance, a dust particle striking the microphone seemed like a plausible explanation for a brief pop that appeared and then vanished. But when researchers examined the waveforms in detail, they realized the situation was not so simple. These events did not display the characteristics of ordinary mechanical impacts. They appeared almost instantaneously, released their energy over an extremely short period of time, and then disappeared completely. That behavior made the dust impact hypothesis less convincing. Another possibility was also considered. Could these signals be electromagnetic interference generated by the rover's own electronics? Perseverance carries hundreds of electronic components, onboard computers, radio transmitters, and scientific systems that operate continuously. In some cases, such systems can generate unwanted signals in sensitive sensors. But, once again, the data did not support that explanation. No unusual electronic events were recorded at the same times the signals appeared. No subsystem showed abnormal behavior. There was also no evidence that the rover's electrical systems produced similar pulses under other conditions. After multiple rounds of investigation, the research team reached an important conclusion. No system on Perseverance could be identified as the source of the signals. The mysterious events appeared to occur more frequently during periods when the environment surrounding Perseverance contained higher than normal amounts of dust. For the first time, the evidence began pointing toward a source located outside the rover itself. After ruling out explanations related to the rover itself, the investigation began moving in a different direction. The question was no longer what Perseverance had recorded, but under what conditions those signals appeared. When all 55 events were placed on the same timeline, they no longer looked random. Many of the signals occurred during periods when the environment around the rover contained higher than normal levels of dust. Others appeared close to times when Perseverance observed dust devils moving across Jezero crater. Dust devils are rotating columns of dust that form when warm air near the ground rises and begins to spin. On Mars, they can range from a few dozen meters to more than a kilometer in height. Some dust devils observed by orbiting spacecraft have measured hundreds of meters across and left dark tracks stretching for many kilometers across the planet's surface. Jezero is one of the regions where this phenomenon is frequently observed. For the first time, researchers identified a clear connection among events that had previously seemed unrelated. If the signals tended to appear when the atmosphere became dustier, the source might not be inside the rover's systems at all. It could be coming from the surrounding environment. For decades, scientists have suspected that Martian dust can become electrically charged as particles continuously collide with one another. On Earth, constant collisions between particles can lead to the buildup of electric charge. Inside a Martian dust devil, billions of dust grains are undergoing the same process. If enough charge accumulates, small-scale electrical discharges could occur within the dust column. Some earlier theoretical models predicted that electric fields inside Martian dust devils could reach tens of kilovolts per meter, potentially strong enough to generate small electrical discharge events. This hypothesis also matched the characteristics of the signals recorded by Perseverance. The mysterious signals did not resemble mechanical sounds. They appeared almost instantaneously, released energy over an extremely short period of time, and then vanished completely. Those are the same characteristics that small electrical discharges often leave behind when detected by highly sensitive recording equipment. Of course, correlation is not evidence. But turning a hypothesis into a scientific explanation requires more than identifying patterns in data. Researchers needed to reproduce the phenomenon under controlled conditions and determine whether the same type of signal would appear. And that became the next step in the investigation. The mysterious signals may be linked to electrical discharges generated when Martian dust accumulates electric charge inside dust devils or small dust storms, but observational data only revealed a correlation. It did not prove a cause and effect relationship. If the hypothesis was correct, the research team needed to be able to reproduce a similar signal under controlled conditions on Earth. That is why they decided to recreate the phenomenon in the laboratory. Rather than searching for additional signals on Mars, they attempted to generate the signal themselves by simulating the charging process of dust particles. A replica of the SuperCam system was used to record what happened when electric charge was generated and released within the experimental environment. The goal of the experiment was not to create a large lightning bolt. In fact, if the signals recorded by Perseverance truly originated in the Martian atmosphere, the phenomenon was most likely composed of extremely small electrical discharges. They could be far weaker than a lightning strike on Earth, yet still powerful enough to produce a brief pulse detectable by the microphone. As particles were made to rub against one another and accumulate charge, electrical discharge pulses began to appear. The only question was whether the resulting signal would resemble the data from Mars. The signals recorded in the laboratory shared many characteristics with the pop sounds detected by Perseverance. They appeared extremely rapidly, released energy over a very short period of time, and then disappeared almost immediately. On the data plots, the two types of signals displayed a number of striking similarities. This did not mean the mystery had been completely solved. A laboratory experiment cannot perfectly reproduce the Martian environment. Atmospheric pressure, air composition, dust density, and countless other factors are different. However, for the first time, the investigation had something it previously lacked: a physical mechanism capable of producing the same type of signal. This model directly linked the buildup of electric charge within dust to the signals recorded by the microphone. Dust collides with dust. Electric charge gradually accumulates. When the stored energy reaches a critical threshold, an electrical discharge occurs, and the microphone captures its signature. Even so, one important problem remained unresolved. Up to this point, all of the evidence came from the region surrounding Perseverance. If the phenomenon truly existed within the Martian atmosphere, it would be far more convincing if an entirely independent source of data had also detected similar evidence. And just as the investigation seemed to be approaching the limits of what the rover could provide, another piece of the puzzle emerged from orbit around the red planet. A signal lasting less than half a second, yet one that could play a crucial role in validating the entire hypothesis. If the investigation had stopped with the data from Perseverance, the final conclusion would still have faced a major limitation. All of the evidence would have come from a single source. One microphone recorded unusual signals. One research team analyzed the data. One laboratory experiment on Earth produced similar results. While researchers were working to explain the signals recorded by Perseverance, another team was examining data collected by MAVEN, the orbiter that has been studying the Martian atmosphere since 2014. Unlike Perseverance, which operates on the surface, MAVEN observes the planet from orbit, monitoring how the atmosphere interacts with the surrounding space environment. While reviewing more than a decade of data, researchers discovered a very rare signal. It lasted only about 0.4 seconds before disappearing. Unless someone was specifically looking for it, the signal would have been almost impossible to notice amid the enormous volume of data collected by MAVEN. The nature of this new signal is what captured the researchers' attention. It was identified as a Whistler wave, a type of electromagnetic wave that has been detected on several other planets throughout the solar system. On Earth, such signals are often associated with electrical discharge events occurring in the atmosphere. They've also been detected on Jupiter, Saturn, and Neptune, worlds where atmospheric electrical activity has long been confirmed. That does not mean every Whistler wave is direct evidence of lightning, but its appearance on Mars was consistent with the hypothesis emerging from the Perseverance data. At the same time, the MAVEN observations raised another question. If this phenomenon truly exists on Mars, why was only a single signal detected during more than 10 years of observations? The answer may lie in the unusual magnetic environment of the red planet itself. Today, Mars no longer possesses a global magnetic field like Earth's. The system that once protected the planet from the solar wind disappeared billions of years ago. What remains are isolated pockets of magnetized crust scattered across the planet. This makes Whistler wave signals far more difficult to detect. For such a signal to be recorded, multiple conditions must occur simultaneously. An electrical discharge must happen at exactly the right moment. MAVEN must be passing through the correct region. The local magnetic field lines must allow the signal to propagate in a direction that can be measured. If even one of those conditions is not met, the entire event can disappear without leaving a trace. As a result, finding only a single signal does not necessarily mean the phenomenon is extremely rare. It may simply reflect how difficult it is to observe. By this point, the investigation had begun drawing on two completely independent sources of data. One came from the surface of Mars, where Perseverance recorded 55 mysterious signals during nearly 4 years of operations. The other came from orbit, where MAVEN detected a brief Whistler wave hidden within more than a decade of observations. Yet both sources were pointing toward the same possibility. The possibility that small-scale atmospheric electrical phenomena exist within the Martian atmosphere and have previously gone largely unnoticed. If these small electrical discharges are real, they are no longer merely an isolated audio anomaly. They become part of the physical processes actively occurring within the atmosphere of Mars. If the current hypothesis is correct, these signals are merely traces of a much larger process taking place within the Martian atmosphere. What truly matters is the process that produced them. For years, scientists viewed Martian dust primarily as an engineering challenge. Dust covers solar panels, clings to equipment, and reduces the efficiency of many systems operating on the surface. But if dust continuously accumulates electric charge and generates small electrical discharges, it becomes a direct participant in the physical processes occurring within the atmosphere. Today, the Martian atmosphere is extremely thin, with a surface pressure of only about 1% of Earth's atmospheric pressure at sea level. In such an environment, phenomena that we are familiar with on Earth do not always occur in the same way. That is why, for many decades, the question of whether Martian dust can generate atmospheric electrical activity has remained unanswered. If small electrical discharges truly occur within dust devils or dust storms, they could directly influence the chemistry of the surrounding environment. Every time an electrical pulse is released, its energy interacts with molecules in the atmosphere and on the surface. On Earth, similar processes contribute to a wide range of chemical reactions in the air. On Mars, such reactions could influence environmental chemistry in ways that scientists are still working to understand. One of the factors that has attracted significant attention is the presence of powerful oxidizing compounds on the Martian surface. Spacecraft have detected various chemicals capable of breaking down or altering organic molecules over time. That makes the preservation of organic compounds on the surface far more difficult. If organic molecules once existed on the surface of this planet, they may have been exposed to a harsh environment for millions or even billions of years. Radiation from space is one challenge. Powerful oxidizing chemicals are another. And if ongoing electrical discharges help generate or maintain some of those compounds, the Martian environment may be even more hostile than previous models predicted. That is also one reason many current missions prioritize studying samples buried beneath the surface. The deeper you go, the less exposure materials receive from radiation, chemical reactions, and environmental processes occurring on the planet's surface. But this is not the final conclusion. At present, there is no evidence showing that these small electrical discharges are the sole source of the oxidizing compounds found on Mars. However, they are emerging as a mechanism that may contribute to shaping the planet's chemical environment. They may represent traces of a physical process that has existed within the Martian atmosphere throughout decades of observation, but has only recently begun to be recognized. Because although the evidence is gradually coming together into a coherent story, no one can yet say with absolute certainty that the final answer has been found. What is certain right now is that a microphone designed to study rocks has opened an entirely new avenue of research into the environment of Mars. Looking back at the investigation, another question emerges. If these small electrical discharges truly exist on Mars, why did it take so many decades to obtain the first reliable evidence of them? Even with an instrument operating continuously for years, the chances of detecting them remain extremely low. The Martian atmosphere makes detection even more difficult. With atmospheric pressure measuring only about 1% of Earth's, any electrical discharge may occur in a way that is completely different from what we are familiar with. Instead of producing easily visible lightning bolts like those on Earth, electrical discharges on Mars are far more likely to appear as extremely brief pulses hidden within moving clouds of dust. They are too small to be easily seen and too rare to appear consistently in front of scientific instruments. That also helps explain why previous missions were unable to provide a clear answer. Orbiters observe the planet from above, but they are rarely in the right place at the right time. Landers, on the other hand, generally did not carry instruments capable of detecting this type of signal. Only when Perseverance landed in Jezero crater with a microphone operating continuously over multiple years did the first clues begin to emerge from the data. It may be a phenomenon that has existed on Mars for billions of years, yet has only recently begun leaving traces clear enough for humanity to recognize. Not because it was too far away, but because it was too small, too brief, and appeared only when every condition happened to align at exactly the right moment. From 55 signals that lasted only an instant, the investigation led scientists through years of analysis, experimentation, and verification. To this day, no one can say with absolute certainty that the mystery has been completely solved, but the evidence gathered so far is gradually converging on the same hypothesis. The brief signals recorded by Perseverance may not be merely an isolated acoustic phenomenon. They could represent the first evidence of small-scale atmospheric electrical processes occurring within the Martian environment. Thank you for staying with Astrexo all the way to the end of this journey. If you enjoy discovery stories like this, be sure to like the video, share it, and leave your thoughts in the comments below. Don't forget to subscribe so you won't miss the adventures ahead. Your support is what motivates Astrexo to continue researching and bringing you even more fascinating stories of exploration and discovery throughout the universe. I'm Astrexo. Thank you for watching, and I'll see you in the next video.